Okay, now for number 6. A sound wave consists of a compression and also rarefaction. Okay, explain the terms compression and rarefaction. Give your explanation in terms of the spacing of the molecules and the pressure for the sound wave in air. Okay, for this question, let me explain to you in the form of pictures. Okay, here is my simple drawing here. Okay, now there is two types of illustration that will be used by a textbook school teachers. Okay, so one is they'll be using a silky spring over here. So it represents the atoms which is in rarefaction mode. Rarefaction means it's like they are far apart. Each atoms here will be far apart. Same goes to this. It's a rarefaction and it is a rarefaction. Okay, so since the atoms are actually far apart, so the pressure here will be lower. Okay, so I just put here low pressure. Okay, however, if you look at the another part of this atom arrangement here, the one that I circled in the green color, this is modular compression. Okay, in this compression, the atoms are actually is arranged in very close together. Okay, and the pressure here will be high. So here we will have a high pressure. So I hope you can understand this basic concept over here of rarefaction and also the compression. Now let me answer the question. Okay, here is my answer suggestion. For compression, atoms are close together and will be in a high pressure. However, for the rarefaction, molecules is further apart from each another and will be in a low in pressure. As long as you have these 2 points, and you can make your own sentences. So you'll be getting a 3 marks over here. Now let us look at the next question. Okay, now if you notice this is some calculation. Okay, a musical instrument emits a sound. Emit means they are releasing or produce. Okay, a sound with a frequency of 4.4 kilohertz. The speed of sound in air is 340 meter per second. Okay, to calculate the wavelength of a sound, so we have this V equals to frequency multiplied with lambda. So this is the wave equation, we call it. Okay, so we can actually substitute this. Speed is 340 and the frequency we just change it to hertz. So it means like multiply with 1000. So you got the 4400, and here we'll be having lambda. Lambda is the wavelength. So we have to divide this. So 340 we divided with 4400. So lambda here we will be getting, let me calculate this, 340 divided by 4400, and we'll be getting here 0.00773. So you can make it like 0.077 meter. Alright, so this is your calculation for 3 marks. Now let us look at the next question over here. Okay, the frequency of the sound emitted by the instrument is changed to 5.1 kilohertz. Okay, if you notice, the previous one is 4.4 kilohertz. This is the frequency, and then they change it to 5.1 kilohertz. Okay, and then the amplitude of the sound, if you look at here, the amplitude of the sound increases. Okay, now if the amplitude of the sound increases, without calculation state what happened to speed of the sound. So the speed of the sound remains constant. Okay, this one is always remains constant. If it's in the air, they remain it as a 330 to 340 meter per second. If in water, it will go about 1500. If in solid, it will go about 3 to 5000 is the speed. Okay, now when you're looking at the wavelength, okay, now there's a simple concept over here. When you're looking at a wavelength, let me draw like a few graphs here. Okay, now 1, 2, 3 and 4. Okay, let us assume that it is about 1 second and here's about 2 seconds. So this is what we call it as a lambda, 1 lambda. Okay, 1 lambda is the wavelength. Now, when you're talking about increasing the frequency, right? Okay, try to imagine when you're increasing the frequency, what happened? Let's say the frequency makes it double. So it's not a really proper graph. So sorry for the drawing size. Okay, 1, 2, 3 and 4. Okay, I managed to make it double. Okay, now when I change the frequency, this one is a higher frequency. Okay, here is a higher frequency. So you can notice that the size of the lambda, the wavelength here is getting shorter, right? So when the speed is constant, according to this formula, so when the frequency is increasing, your lambda should be, the wavelength should be reduced. So you can say the wavelength of the sound here is it decreases. So these are the explanation for this question. So here's 2 marks and total is about 8 marks over there. Okay, so I hope you're okay with this one. So let us move to the next question. Okay, now for the question number 7, state 2 uses of infrared radiation. Okay, this question is about electromagnetic waves. Okay, so one of the uses is about remote control. If you look at our car remote control or remote gate or remote anything to do with sensors, okay, so they'll be using infrared radiation. So we can put the answer here as for remote control. Remote controls, and we can also add in and sensors. Okay, so all the sensors and alarms, they're using infrared radiation. The another application here that we can think of is a thermal imaging. So let me show you what is a thermal imaging. Okay, let me open my Google here. Okay, now the thermal imaging. Okay, it looks like this. Okay, it looks like this. So these are the thermal imaging, the image that appeared from the thermal imaging cameras. Okay, so they will detect the heat from the person and you will have the images like this. Okay, so now we go back to the question. Okay, now we will have X-ray used in hospitals to help treat patients. So suggest and explain the 3 precautions for the safe use of X-ray. Okay, the first thing here that you can see like one of the precautions, right, for the safe use of X-ray, you can mention that limit the usage time. Okay, limit the usage time, or you can also say the time of exposure. Okay, number 2, you can also like adjust the intensity of this X-ray, where you can limit the dosage. Okay, the dosage used. Or we can also mention it as intensity used. Okay, the third one. Okay, the third one here you can mention. So when because you are not going to use the X-ray for the whole body of the patient, right? So you can actually normally they'll use X-ray for the certain part of the body. So the rest of the part we can actually protect it by using a shielding method. So we can like use a shield shielding of the other parts of the body that is not used for this X-ray. Okay, we look at the next question here. Okay, state the speed in a vacuum of a microwave and X-ray. Okay, please remember that this is a electromagnetic waves. So as a small explanation about this electromagnet, so let me explain to you. EM stands for electromagnet. Okay, we will have like a 7 types of rays. Okay, 7 types of rays. So one of it is a radio, and then we will have a micro. So and then the third one is we have a infrared. Okay, infrared. The fourth one is a visible light. Visible light for the photosynthesis. How we you can see me and I can see you. And here is the UV light, ultraviolet, and here is the X-ray, and here's the gamma ray. So it's a short explanation. Okay, now the radio wave, we are using it for the TV and the radio's transmission. All right, so this is a radio wave. They have a longest wavelength. Okay, so they have the longest lambda wavelength. Micro, they are using it for the cellular, for your phone communication. Okay, so I just put there like a cellular communication. Other than cellular, we are also using it for oven, okay, to bake cookies. Or okay, for infrared, I have explained just now, is for the sensors. Visible light for the photosynthesis, and how I can see you and you can see others. We are using visible light. UV, the UV is to detect the fake notes. Okay, sometimes they are using it for the agriculture purpose. Okay, and then the X-ray is to treat cancer cells, or they can also detect bones and detect the hidden objects in a building. Okay, for bones X-ray. Okay, the gamma ray, normally they'll be using a gamma ray to kill cancer cells. This is we call as a radiotherapy. Okay, there's another medication they're using is a chemotherapy. Okay, so these are the basic of the electromagnetic rays, and all of their speed is 3.0 times with 10 to the power of 8 meter per second. So these are their speed. They are following the speed of light. Okay, now let us go back to the question here. Okay, so now for microwave and X-ray, they have the same speed, which is this meter per second, and same goes to here. Okay, now state the possible frequency of an ultrasound. Okay, our normal human hearing range is a 20 Hz to 20,000 Hz. So ultrasound means it's something extra. So it will be higher than 20,000. So we can just state there about 25,000 Hz, or anything actually more than 20,000 Hz is a ultrasound. Okay. So the total marks for this question is 8 marks. So we can move on with the next question over here.